Welcome to another video from HEGARTYMATHS. In this video we are doing integration by parts. And by the end of this video I'd like us to be able to integrate functions using integration by parts, this new technique I'm going to show you. And it's like the reverse of the product rule. Okay, so I'd like you to think of it as the reverse of the product rule, and that's how I'm going to introduce it. So let's suppose, let's think about the product rule and differentiation. Now suppose you had something like u of x multiplied by v of x, and we wanted to differentiate this thing. D by dx means I'm going to differentiate this thing here. Now by the product rule, you know that's equal to u of x multiplied by v dash of x, the differential of v, plus v of x multiplied by the differential of u of x, where u and v are functions of x. Okay, and sometimes we wrote that without the x's in it. We just said that if we wanted to differentiate two functions of x, u and v multiplied together, okay, where u and v are both functions of x, it's u v dash plus v u dash. Okay? Okay, so this is the product rule for differentiation. Now suppose, okay, suppose I integrated both sides. Now suppose what I did is I integrated both sides. So I integrated d by dx of u of v with respect to x, and I integrated u v dashed with respect to x, and I integrated v u dashed with respect to x. Okay, then this would hold true because I can integrate both sides. But the key thing here is integrating after you've differentiated something just undoes the process of differentiation. So this thing here, because integration and differentiation are the opposite processes, this is just going to be uv. So u multiplied by v is going to be the integral of uv dashed with respect to x plus the integral of v u dashed with respect to x. Okay, now how this turns out to be useful, in fact, it turns out to be useful in this case. Suppose we had, if I made, in fact, this the subject of the formula. So I'm going to make this thing here the subject of the formula, so that I had the following. I'm going to say that the integral of u v dash with respect to x is going to equal uv subtract this. So uv subtract the integral of v u dash with respect to x. And the other thing I'm going to need, if these are indefinite integrals, there's no limits on them, I'm going to have a constant of integration here as well. It will be a constant on both sides, but I could just write it as one constant on one side. Now, say I rewrote this as this. We know this is true. Now, say if I rewrote this in this form here, this so happens to turn out to be a really useful way of integrating. And the reason it is if you ever have two functions multiplied together, like this, so you've got a function multiplied by another function, and one function you can easily integrate, so you can make the v dashed into a v, and the other function you can easily differentiate. You can make the u into a u dashed, and this is an easier integral to solve than the original. Then you have a way of working out this harder integral. Now at the moment it seems pretty sort of abstract, but let me just say for now that the formula we're going to use is the integral of u v dashed with respect to x is going to equal u multiplied by v, the original functions, subtract the integral of v u dashed, okay, with respect to x. And if it's an indefinite integral, we're going to have a plus c. If it had limits in it, say if it had limits, let's say a and b, with respect to x, it would be uv worked out at b and a, subtract the integral of a to b of v u dash with respect to x with no constant. So these are the two rules we're going to use. And when are we going to use them? Well, the things that make us think to use them is, one, if you've got a product, but there are many things with a product where you wouldn't use this, but u and v dash, you've got two functions, a product of two functions. That may indicate to you that you might use it. And secondly, of the two functions, for the two functions, one of them easy to differentiate, one of them easy to integrate, and also when you have done that, it turns out that the integral of vu dash with respect to x is something you can integrate. Okay, so there are a lot of conditions here, but we'll only start to see it when we do a few examples. So let's have a go at the first one. We're integrating x cos x with respect to x. Okay, now firstly, is this a standard result that I know? No, x multiplied by cos x isn't. Is there any other thing I could use, like by inspection or anything like that? No, not really. So I'm thinking to myself, well, hold on, it's of the form two functions multiplied together. Okay, so I'm going to try and use the integral, this formula of u v dashed is going to equal be u multiplied by v, subtract the integral of v u dash. Now the question is, what do I choose to be my u, and what do I choose to be my v dash? The thing that I want to be my u is something that is easy to differentiate and makes the answer, this integral over here, easier. And the thing I make my v dash is the thing that's easy to integrate and also keeps things simple. So, if I let my u be x, and if I let my v dash be cos x, could I work out u dashed and the original v? Now to work out u dashed, I differentiate this and I get 1. To work out v, having got v dashed, I integrate cos x and I get sin x. Okay? What is this integral that I'm trying to work out? I'm trying to work out the integral of x cos x dx. And using the formula up here is u multiplied by v, so u multiplied by v, so it's going to equal x sin x, subtract the integral of vu dash, so sin x multiplied by 1, so the integral of sin x multiplied by 1 with respect to x. Now the beauty of this is, I can integrate, this is just sin x, I can integrate sin x, it's easy for me to integrate, it's negative cos x. So this integral here is going to be x sin x, subtract negative cosine x, plus your constant of integration. So that's going to be x sin x plus cosine x plus your constant of integration. Okay, and we're done. So that's the integral of x cos x dx. Now, let's just have a quick think over here. So I'm just going to do a little quick think over here. What if I chose my u and my v dash differently? What if I said my u was equal to cosine x and my v dash was equal to x? Then my u dash, well, I can differentiate that easily. It's negative sine x, but my v would be a half x squared. And if I applied this formula here, uv multiplied by, subtract the integral of vu dash would be a half x squared sine x, a negative of that, which I can't integrate easily. I've just made that more complicated. So the important thing here, the important lesson, is I choose my v dashed. Now hold on, I choose my u so that u dash v is easy to integrate, So I choose my u and really my v dash so that uv dash is easy to integrate. If it isn't easy to integrate, there's no point in doing the method. I've just made a more complicated integral for myself. Okay, so let's have a go at another one. Let's integrate x squared ln x with respect to x. It's a product. So I'm thinking, because it's not something I recognise as a standard integral, I'm thinking integration by parts. An integration by parts is the integral of uv dash is equal to uv subtract the integral of vu dash. Okay? Now, the key is, what do I choose to be my u and what do I choose to be my v? Now, so what's my u and what's my, v dash? Now, whatever I choose to be my v dash, I have to be able to integrate it. And as such, I don't know the integral of ln x. Okay, I know the differential of ln x is 1 over x, but I don't know the integral of ln x. So ln x wouldn't be a good choice for this, so x squared is going to be the best choice. Whereas u, I'm going to have to be natural logarithm of x, because I can differentiate that, and u dash is going to be 1 over x. So v, in this case, integrating x squared is going to be a third x cubed. So let's therefore try and integrate x squared, natural logarithm of x dx, is going to be uv, so these two multiplied, a third x cubed natural logarithm of x, subtract vu dashed, so it's going to be this multiplied by this, which would be the integral of a third x cubed multiplied by 1 over x dx. Now the beauty of doing that is the 1 over x and the x cubed, they cancel to x squared. So I've got a third x cubed natural logarithm of x, subtract, I'm going to take the third out, a third the integral of x squared dx. Now let's integrate this, so it's a third x cubed natural logarithm of x, subtract the third, and this would be a third x cubed plus c. And so what would I get? Well, I'd get a third x cubed natural logarithm of x, subtract a ninth x cubed plus c. And there we go, that is how I did this. Now, if I had chosen my v dash to be ln x, I didn't know the integral off the top of my head of ln x. So it looks, one, I couldn't do it, and secondly, it would have made it more complicated. The beauty of using this method is that it made this integral simpler and something I could work out. Okay, let's have a go at another one. We want to integrate x squared e to the x. So it looks like a product, an x squared multiplied by an e to an x. So I'm going to try integration by parts, which says the integral of uv dash is equal to uv subtract the integral of vu dash. Okay, now the question is, what to be my u and what to be my v dash? U has to be something I can differentiate, and I could differentiate both of these. V dash has to be something I can integrate, and I can integrate both of these, but v will end up in the second part of the integral. Now if I chose my v dash to be x squared, and I got my v to be a third x cubed, u dash, this would have a third x cubed and an e to the x in it. That is not easier to differentiate, that's made it more complicated. So I know I'm not going to choose those two to be in here. So what I'm going to choose is I'm going to choose my e to the x to be in here. So that's e to the x, and if I integrate e to the x, I get e to the x. So my u is going to be x squared, so my u dashed is going to be equal to 2x. So let's apply this formula. The integral of uv dash, which is x squared e to the x with respect to x, is going to be uv, so it's going to be x squared e to the x, subtract vu dash, so these two, subtract the integral of 2x e to the x with respect to x, which what I can do is I can rewrite as x squared e to the x subtract 2 integral x e to the x dx. Now I actually don't know how to integrate this. I don't actually know how to perform this integral, but it's certainly got simpler from the one I started with. The one I started with had an x squared e to the x dx. Now we've just got 1x e to the x. So what I can actually do is I can do integration by parts on this thing again and get an expression for that. So the integral of x e to the x dx would be, and this time, actually if I go down a little bit, I've been a bit too hasty, I'm going to start a new working. That's what I'm trying to work out. And what I'm going to do is I'm going to start off and set a new u and a new v dash. So my u is going to be x again, so that my u dash is 1, and my v dash is going to be e to the x again, so my v is e to the x. So this thing here would be the integral of uv, which would be x e to the x, subtract the integral of vu dash, which is the integral of 1 multiplied by e to the x dx, which is just e to the x. So this thing here is x e to the x, subtract e to the x plus a constant. Okay, so there's my separate bit of working, and I could replace this in here now. So going back here, so I could call this a working, and I could write working here. So therefore the integral of x squared e to the x with respect to x, well, it's still this thing here, it's still x squared e to the x, and it's subtract 2, the answer to this thing, and this thing was x e to the x, subtract e to the x, and don't forget at the very end your constant of integration. So just tidying that up, it would be x squared e to the x, subtract 2x e to the x, add 2 e to the x plus constant. And that is the integral of x squared e to the x dx. And just to remind you, in this case, what I had to do is I had to integrate by parts twice there. Okay? Another example. Find the integral of the natural logarithm of x with respect to x. Now, this is one of those little trick integrals you've just got to remember. When you're integrating the natural logarithm of x, something we don't know how to do yet, integration by parts gets you the answer. But there's nothing multiplied together. Well, there can be if you're just a little bit clever about it and you write that as the integral of 1 multiplied by the natural logarithm of x dx. And then we can try and use our formula. The integral of uv dash is uv subtract the integral of vu dash, choosing our u and our v dash appropriately. So what should my u be and what should my v dash be? Well, u has to be something I can differentiate. I can differentiate 1 to 0, but then I don't know if I chose my v dash to be ln x, I can't integrate that. That's the whole point. I don't know the integral of this. So I'm going to have to choose my u to be the natural logarithm of x, which I can differentiate as 1 over x. And my v dash I'm going to choose to be 1, which I can integrate to equal x. So applying this formula, the integral of 1 multiplied by the natural logarithm of x dx is going to be u multiplied by v, which is x natural logarithm of x, subtract vu dash, which is x multiplied by 1 over x. So it's going to be x multiplied by 1 over x dx. And x multiplied by 1 over x is 1. So this is the integral of x natural logarithm of x, subtract x, and then we're going to have ourselves plus a constant. So the integral of the natural logarithm of x with respect to x is x natural logarithm of x, subtract x, plus 1. And we're done here. Now I'm going to move on to this example here. This is almost identical apart from we've got limits. So here we've got limits in our answer. Now we can do the exact same thing. We're going to integrate that by parts. I'm going to write that as the integral of 1 to 1 multiplied by the natural logarithm of x with respect to x. And I'm going to use the formula, the integral of uv dash is going to be the uv subtract the integral of vu dash. But the difference here is I've got limits, so I'm going to put it between a and b here. I've got limits here, so I'm going to evaluate these two at limits a and b and work out this integral at a and b. That's the only difference here. So in this question, before I've already done this, I've chosen my u to be natural logarithm of x, so that u dash is 1 over x. I chose my v dash to be 1, so that my v is equal to x, and therefore applying the formula, the integral between 1 and 2 of the natural logarithm of x with respect to x is going to be u multiplied by v, so x natural logarithm of x, evaluated between 1 and 2, subtract the integral between 1 and 2 of u dashed v, which is just 1 with respect to x. So this would be x natural logarithm of x evaluated between 1 and 2, take away the integral of this, which would be x evaluated between 2 and 1. Now there's no plus c here because it's a definite integral. Now the question asks us to leave our answer in terms of natural logs, so substituting in 2, it would be 2 log 2, subtract 1 log 1, take away, and then take away, so all of that, take away, what do we get here? 2 and take away 1. So this is going to be log 1 is 0, so this is just going to be 2 log 2, and then 2 take away 1 is 1, so subtract 1. And we can leave our answer in that form. We could obviously bring the 2 up if we wanted and write that as log 4 take away 1 as well, but it doesn't matter. Both of these are the right answer. Okay, so we're nearly done now. The last thing just to point out is, don't forget, in the formula booklet there are various integrals given to you in the formula booklet that might be useful in an integration by parts, something that you can integrate. So you can choose to be, let's say, your v dash, because it's an integral that's given in the formula booklet. So these are ones that I picked out. Let's just have a look at this example here. Okay, it's a product. It's not something I can easily integrate, so I'm thinking to use integration by parts, i.e. I'm thinking to use the integral of uv dash is uv subtract the integral of vu dash, and between limits in this case, so between a and b, this evaluated between a and b, and this between a and b, so I'm going to use that. There's no plus c here. Now the question is, what do I let be my u, and what do I let be my v dash? I can differentiate and integrate that, so that's not the problem to me. Can I differentiate or integrate that? Well, look in my formula booklet, okay, I can see the following. I can see that if I integrate tan x, I get ln sec x. So going backwards, if I differentiate ln sec x, I get tan x. So it would be best if I chose my u to be ln sec x, because then when I differentiate it, I would get tan x. Now my v dash, that's sine x, and when I integrate sine x, I get negative cosine x. So let's just check the reason I chose this. I chose this to be the thing I differentiate because that's what I know how to differentiate. Because I know the integral of tan x is ln sec, so the differential of ln sec is tan. So they were using the results in my formula booklet. So let's apply the formula. So I'm integrating between 0 and pi by 3 sine x multiplied by ln sec x with respect to x. So it's going to be u multiplied by v, so it's going to be ln sec x multiplied by negative cosine x, and that evaluated between 0 and pi by 3. And you're going to take off vu dash. So I'm going to take off these two things multiplied together. So I'm going to take off the integral between 0 and pi by 3 of tan x negative cosine x. So that negative, I'm going to bring it out and make that plus cosine x with respect to x. Now, the reason that's helpful, let me just keep this as it is before I start working stuff out. The reason that's helpful is tan x. Remember, tan x is sine over cos. So sine over cos multiplied by cos is just sine. So that's the integral between 0 and pi by 3 of sine x with respect to x. And I can integrate this. So that's the beauty. From something I can't integrate, I can now integrate this. So let's, before I put limits in, let me integrate the whole thing. So that's sec x cosine x between 0 and pi by 3. And the integral of sine x is negative cosine x. So this would be subtract cosine x between pi by 3 and 0. So now it's just a case of substituting these things in. Okay, now sec is 1 over cos. This thing here is 1 over cos. So 1 over cosine of pi by 3. If I put pi by 3 in, pi over 3 like that. Well, actually, I should know that one. It's best if I just go over here and do some separate working. So working, I know that cosine of pi by 3, cosine of 60, should equal a half. Actually, the reason that didn't work is it was in degrees mode. So if I go mode and I go radians, just thought it would be 2. The cosine of pi by 3 is a half, so sec of pi by 3, anyway, I should have probably done it without a calculator, is 2. So this is going to be, putting in pi by 3 is negative ln of 2. So negative ln 2, and cosine of pi by 3 is equal to a half, multiplied by a half. Okay, and then I'm going to take off the answer when I put 0 in. Now, cos of 0 is 1, and ln sec is therefore 1, and ln of 1 is 0. So I know this whole thing without even working out that is going to equal 0 like that. And then I'm going to take away the answer when I put pi by 3 in. Now cos of pi by 3 in I said was a half, and then I put 0 in, and cos of 0 is 1. So it's going to look like that. So therefore I get negative ln half ln 2, negative a half ln 2, and then I'm going to have subtract a half take away 1 is negative a half. So I get myself a half. This here is going to be plus a half take away a half ln 2 as follows. And I can factorise that and I can say that's a half 1 subtract ln 2, and I'm done. So that's my integral in this case. Now obviously what I can do is I can use the calculator to check that. Hopefully the calculator will be available to check that. So I can get the calculator out and I can ask it to integrate. Sorry, I can ask it to integrate sine x, so sine x, ln sec x, so ln, and then sec x is 1 over cos x. So I'm going to write that as 1 divided by cosine x, close that bracket and go up there and close that. And I'm going to integrate it between 0 and pi by 3, so pi over 3. Now sometimes the calculator takes a while to do this, but hopefully this will find the answer for me. So if I press equals there and I let it go on, it says that the answer is equal to this. So it says the answer is equal to 0.153426 4097, and what I could do is I could check this is equal to the same thing. So if I worked out a half 1 subtract natural logarithm of 2, I get 0.15342797. So I know that the answer I got is right, and that's a perfect use of the calculator in the exam to check these complicated questions. Anyway, I'm done now for this. And in order for you to consolidate your work, I'd suggest you do the following. Thanks for watching.